Hello, my name is Kevin Boos, and I'm a researcher from Rice University. Today I'm going to talk about Theseus, a new operating system we've created from scratch to experiment with the structure of and state management within operating systems, and also how we can leverage the power of modern safe systems programming languages while doing so. This work was done in collaboration with my colleagues at Rice and Yale University, Namitha, Ramla, and Lin. In this work, the key research hypothesis guiding our OS experimentation is whether fundamentally redesigning an OS to avoid state spill will make evolution and fault recovery of the OS components easier. And as we began to build the system, a deeper question arose about how much modern systems programming languages and compiler-enforced safety can help. Initially, this line of work was motivated by a study of state spill, the phenomenon in which one software component harbors changed states as a result of handling an interaction from another component, such that the future correctness of those components depends on those changed states. State spill is quite prevalent in modern system software, and it leads to fate sharing between software components that are otherwise modularized and isolated. This hinders the realization of several challenging yet desirable computing goals, things related to availability, like fault isolation, tolerance, and recovery, and things related to evolvability, like live update and maintainability, as well as other goals. As a simple example, consider two applications interacting with an OS service. As a result of handling an interaction from App A, the OS service now holds states relevant to that client App A. Similar changes in the service state occur after interacting with App B. Now, if the service crashes and then restarts, as is the default recovery procedure in most systems, those states representing the progress of App A and B with the service will be lost. Or it'll be in an inconsistent state with respect to the application's expectations. This causes undefined behavior in the worst case, or an immediate crash in the best case. Our motivation actually goes beyond state spill too. After experimenting with Rust's ownership model and its safety invariants, we realized that they can be leveraged for more than just writing safe OS code, such as enabling the compiler to check certain correctness invariants for OS-specific behaviors and resource usage. In addition, we are further motivated by two important goals mentioned previously, evolvability and availability, which require additional effort beyond addressing state spill. These abilities are crucial in certain system software domains. For example, the embedded system software in spacecraft, like satellites, rovers, and probes, or in implanted biomedical devices like pacemakers, must be updated without downtime or the loss of context. Even in data center networks, where switches are replicated for reliability, software failures and maintenance updates in the switches still lead to network outages despite this redundancy. We believe that Theseus is well suited for these environments. The outcome of our experimentation along these lines is Theseus, a new OS that we've written from scratch, entirely in Rust. It makes the following contributions. First, it establishes an OS structure of many tiny components, which must all have clear boundaries that persist into and throughout runtime. Second, it follows Intralingual OS design, intralingual meaning within the language, in which we leverage the strengths of the Rust language to empower the compiler to take over common OS duties, such as resource bookkeeping and preventing unsafe or incorrect resource usage. Third, Theseus strives to avoid or at least mitigate the effects of state spill. Theseus has been designed and implemented with evolvability and availability in mind, and it currently consists of just under 40,000 lines of Rust code. These contributions can be put more simply as the design principles that Theseus follows. We'll discuss each one in detail. But first, an overview of Theseus' OS structure. Every component in Theseus is a cell, a software-defined unit of modularity that serves as the core building block of the OS, much like their namesake of biological cells in an organism. Cells are based on crates, which is Rust's project container, that comprises source code and a manifest file specifying its dependencies on other crates. To realize the first principle of runtime-persistent bounds, we dynamically load all component cells within Theseus, not just drivers or extensions, as commonly done in other safe language OSs and microkernel and monolithic systems too. This enables Theseus to construct detailed cell metadata that tracks cell bounds, that is, the location in memory and size of every cell, as well as their bidirectional dependencies on other cells at section-level granularity. This metadata, pictured here on the right, is crucial. It simplifies the logic for cell swapping, which is the key mechanism for evolution within Theseus, and it's also reused for fault recovery. More importantly, all Theseus cells execute in a single address space and privilege level, meaning that everything from top-level apps and libraries to low-level core kernel components are observable as cells. This, in turn, enables Theseus to apply its single cell swapping mechanism uniformly to any cell, and to also jointly evolve cells across multiple layers safely. Theseus' second design principle is to leverage the power of language by enabling the compiler to check safety and correctness invariants to the fullest extent possible. Now, Rust already provides a variety of invariants and built-in rules to ensure safety, such as its ownership model and borrow checker, that ensure the lifetimes of references or aliases don't exceed the lifetime of the object they refer to. For example, the Rust compiler can check for memory-safe usage of objects on the stack and heap because it has a priori knowledge of those. We strive to extend these compiler checks to all OS resources, such as arbitrary memory regions, tasks, devices, and more. Intralingual design can be broken down into two parts, matching the OS's execution model to what the compiler expects, and then using existing language-level mechanisms to implement OS functionality and to express resource semantics within the strong static type system. Since the first part essentially entails using a single address space and privilege level, which I've already discussed, I'll skip to the second part. Intralingual OS design allows the compiler to understand the semantics of OS components and apply its safety checks to them. On a side note, we prioritize the use of safe code above all else, and we only descend into unsafety when it's fundamentally unavoidable. Intralingual OS design requires identifying the invariants for each resource that prevent its unsafe and incorrect usage, and then using only existing language-level mechanisms to express those semantics. This enables the compiler to subsume those invariants into its own and check them by default. We must also use lossless interfaces, such as function calls that preserve all language-level context. For example, type information, lifetimes of references, and the notion of ownership. This allows the compiler to ensure the provenance of language context in order to verify that it hasn't been recreated extralingually or unsafely on one side of the interface, as is the case with system calls when they enter the kernel. Theseus also goes beyond safety to prevent resource leakage by implementing custom stack unwinding. Together with the compiler, this ensures resource cleanup can occur in core OS contexts, even in exceptional execution paths. In combination with Rust's ownership semantics, this relieves the kernel and the OS at large from the burden of resource bookkeeping, which brings us to the ensuing benefits of intralingual design. As such, the compiler can take over resource bookkeeping, which prevents the OS from needing to maintain bookkeeping states, for example, within its task struct. This reduces state spill significantly from other subsystems into the task struct, for example, which strengthens isolation by reducing fault sharing. It also removes the gaps in the compiler's understanding of OS code, which thereby approaches end-to-end safety from applications to core kernel components, and it shifts semantic runtime errors into compile time errors. The third principle Theseus follows is to avoid state spill. We have many techniques to do so, but the key one is opaque exportation. The other details can be found in our paper. Opaque exportation shifts the responsibility of holding progress states from a server to a client component, which is only possible due to type safety, memory safety, and intralinguality within Theseus. The server can then be more easily evolved and recovered from faults because it doesn't hold those client-relevant states anymore. Note that in Theseus, we can still revoke those client-held states using its unwinder, for example, to reclaim an acquired resource. One great example of intralingual and spill-free design is Theseus's mapped pages abstraction, which represents a region of virtual memory pages mapped to physical frames. Mapped pages enables the compiler to uphold many safety invariants for the use of arbitrary memory regions, ultimately preventing things like unexpected invalid page faults. Please check out our paper for more details and examples of intralingual multitasking as well. To realize our first goal of live evolution, we implement the mechanism of cell swapping, a multi-stage procedure that replaces some existing old cells with new ones. In this example, we replace an existing cell C with two new cells, J and K, as shown here on the right. The full details of this procedure and how Theseus' design choices facilitate it are found in the paper. The second goal of availability is realized via fault recovery. Note that many kinds of faults are already prevented by Rust's safety and Theseus' intralinguality. So we focus on recovering from faults induced by hardware beneath the language level, such as random memory corruption. Theseus takes a cascading approach to fault recovery, in which the first stage is to simply clean up and fully unwind a task. which allows the system to tolerate the fault and continue running other tasks. The second stage is to restart a failed task, which we ensure the soundness of by using an interlingual restartable task abstraction described in the paper. The third stage is to completely reload and replace a corrupted cell using the same cell swapping mechanism for evolution. These recovery mechanisms operate with very few dependencies, allowing them to work in core OS contexts, like exception handlers, where microkernel recovery approaches cannot. Our evaluation of Theseus covers case studies of fault recovery, live evolution, the cost of intralinguality and state spill freedom, and more. For example, Theseus recovers from nearly 70% of hardware faults that we inject into it, and it's able to evolve core OS components, even those that must exist within microkernels like an IPC layer, with very little execution delay and no loss of execution context or state. Of course, Theseus is not without its limitations. For example, it relies upon safe language properties for isolation, and it has to trust that the Rust compiler and core libraries are sound. See the paper for a fuller discussion of limitations. In conclusion, Theseus's design specifies a structure of many tiny component cells that are dynamically loaded and linked in order to ensure their bounds persist into and throughout runtime. It follows intralingual design to leverage the power of language and enable the compiler to check OS-specific invariants and to take over resource bookkeeping, which subsequently avoids and mitigates the effects of state spill. Thank you very much for listening. Theseus is open source on GitHub, and it's currently under development. Feel free to contact us with any questions at all. Thank you.